You type a web address into your browser, and you hit enter. In the exact millisecond that key bottoms out, a hidden timer begins. Your machine is now kicking off a massive sequence of computational events. To get the website you requested, data has to travel through a physical medium. It will be pushed through local copper wiring, beamed over radio waves, and fired as light pulses down undersea fiber optic cables. Look at this map. If you are a client sitting in one hemisphere and the origin server holding your data is thousands of miles away in another, the absolute speed limit for this entire operation is the speed of light. To understand how a complex web page renders before you can even blink, we have to deconstruct the exact sequence of protocols, DNS, TCP, TLS, and HTTP, that execute in the few hundred milliseconds before the screen populates. Accessing a web page is never a single discrete action. It is a highly orchestrated series of sequential, round-trip handshakes. The first barrier is routing. Network hardware cannot read human-readable URLs like example.com. Routers require a numerical IP address to know where to send your request. To find that number, your browser first checks its own local cache, scanning its memory to see if it already knows the IP address for this specific domain. If the cache is empty, a recursive DNS lookup begins. The request pings an ISP resolver, then queries root, top-level domain, and authoritative servers to return the IP address 192.0.2.1. This search incurs a temporal cost, burning precious milliseconds simply finding the address. The domain name system is the unavoidable prerequisite of the Internet. Without that IP address, the rest of the protocol stack remains completely dormant. Once the address is known, data transmission can begin. But data does not travel as one continuous stream. It is fragmented into tiny independent units called packets. Each individual packet is wrapped in an IP header. This header contains the specific destination IP address we just retrieved from the BNS lookup. Routers act as autonomous traffic directors, evaluating the most efficient path for each packet based on real-time congestion. A packet navigates hop by hop, often making 10 to 20 distinct router hops to reach its destination network. The physical layer is inherently chaotic. Sequential packets from the same file can take completely different geographic routes, arrive out of order, or simply get lost entirely. The Internet Protocol handles addressing and physical movement. It provides absolutely no guarantee of successful or orderly delivery. To engineer reliability over a chaotic physical network, the system relies on the Transmission Control Protocol, or TCP. This waterfall diagram maps the three-way TCP handshake. The client sends a SYN packet, the server replies with SYN-ACK, and the client confirms with ACK. If a packet drops, TCP notices the missing sequence number and mandates an immediate retransmission. TCP guarantees delivery, but it transmits everything in plain text. Any intermediary router along the path can intercept and read the data. To solve the plain text vulnerability, a mandatory transport layer security, or TLS, handshake must execute immediately after TCP. During this phase, the browser and server exchange cryptographic keys and validate the server's SSL certificate to confirm its true identity. This exchange creates an encrypted tunnel. From this point forward, the upcoming application data is shielded from interception by ISPs, public Wi-Fi routers, or bad actors. Notice the severe latency penalty mapped here. Multiple round trips across continents are required just to establish TCP and TLS, all before a single byte of actual website data is requested. Security and reliability are strictly enforced by mathematical protocols. The primary cost for that enforcement is paid in physical transmission latency. With the encrypted tunnel established, the system finally invokes HTTP, the application layer language browsers and servers use to communicate. On the sequence diagram, the HTTP GET request travels securely through the TLS tunnel to the origin server. The server executes its backend logic, querying databases and rendering templates before firing a response back to the client. That HTTP response carries a status code indicating success, response headers, and the base HTML document. As soon as the HTML arrives, the browser begins parsing it, translating the code into a document object model, or DOM, tree. But the initial HTML file is rarely complete. It usually contains references to external resources required to build the page, style sheets, JavaScript execution files, and images. This geographic map shows the browser spawning parallel HTTP requests to fetch secondary assets. Large websites deploy content delivery networks, geographic edge nodes closer to you, that intercept these requests, serving files locally to eliminate the latency of returning to the origin server. A modern web page is an asynchronous assembly of components. Rendering it instantly requires decentralized geographic servers delivering assets in parallel. Looking at the fully populated sequence diagram, we see the complete lifecycle: the DNS lookup, TCP reliability handshakes, TLS encryption, HTTP delivery, and DOM assembly. The latency paradox of the internet is achieving a sub-second page load while executing numerous physical round trips across thousands of miles of wire. The architecture mitigates this through caching. Browsers, ISPs, and CDNs aggressively cache content locally, so that on repeat visits, you skip the DNS and asset fetching round trips entirely. This topology overlay demonstrates load balancing. Popular sites distribute incoming TCP connections across massive clusters of back-end servers, preventing millions of simultaneous requests from bottlenecking a single origin machine. The internet scales to billions of users by maintaining strict protocol layers for routing, security, and delivery, while engineering architectural shortcuts that respect the hard physical limits of distance and time.